everyone, and welcome. Today we are diving deep into a really cool corner of chemistry. We're going to uncover a secret world of chemical sharing, looking at a special kind of bond that's all about generosity. It's a connection that kind of breaks the rules we thought we all knew.
So think about it. We're usually taught that in chemistry, forming a bond is a partnership, right? Both sides have to bring something to the table. But is that always true? Is sharing always a two-way street? That single question is what we're going to unpack today.
And here it is, the whole idea in a nutshell. On the left, you've got your standard, everyday covalent bond. Super familiar. Each atom puts in one electron, they share, everybody's happy. But on the right, that's our main character today, the coordinate covalent bond. This is where one atom goes, you know what? I got this, and donates both electrons to form the bond. It's one-sided giving.
Okay, so to really get why this generous bond is so special, let's just do a quick refresher on the standard rules of engagement in the chemical world. So the classic covalent bond is all about mutual sharing. That's the key phrase. Each atom contributes one electron to the pair they're going to share. And why do they do this? To become stable, usually by getting a full outer shell of 8 electrons. You know, the octet rule. The handshake analogy is just perfect. It's firm, it's equal, both parties are participating.
All right, you got the standard handshake down? Perfect. Now, let's look at the plot twist. This is where things get really interesting. And here it is, the coordinate covalent bond. You'll sometimes hear it called a dative bond. Now look, it's still a covalent bond, which means electrons are being shared. But its origin story is totally different. The entire shared pair of electrons comes from just one of the atoms. It's not a deal, it's a donation.
And chemists, of course, have a neat little way to show this. Instead of drawing a simple line for the bond, they often use an arrow. And that arrow tells you everything. It points from the atom that's doing the donating, the donor, to the atom that's receiving the electrons, the acceptor. It's a visual map of that generosity.
So for this whole thing to work, you need the right conditions. You need two very specific players to show up on the field, a giver and a receiver.
Let's meet our cast. First up is the donor, our generous giver. Its key feature? It has what's called a lone pair. That's a pair of electrons just hanging out, not involved in any other bonds. It's available. On the other side, we have the acceptor. This molecule is electron deficient. It's got an empty spot, an empty orbital that's just waiting for an electron pair to move in.
So what happens when our generous donor actually bumps into our needy acceptor? Let's watch the story unfold with a classic chemical reaction. Okay, this is the textbook example. You have ammonia, NH3. Its nitrogen atom has that lone pair ready to go. Then along comes boron trifluoride, BF3. Its boron atom is really electron deficient. It hasn't satisfied its octet. So the nitrogen in ammonia sees this empty orbital on the boron and just gives its entire lone pair to it. And bam, a brand new bond is formed, a coordinate covalent bond, and now both molecules are stable.
And believe me, this isn't just some rare one-off thing. It is fundamental to so much of chemistry. When ammonia meets a proton, which is just a hydrogen nucleus with no electrons, it forms the ammonium ion. Same thing with water. The oxygen in water has lone pairs, and it can donate one to a proton to form the hydronium ion, which is absolutely central to how acids and bases work. So, we've seen how this generous bond is born. But this is where the story takes a really surprising turn. Let's talk about the bond's secret identity after it has been created.
Just take a second to let that sink in. All that special backstory we just talked about, the donor, the acceptor, the one-sided donation, the moment the bond is formed, it's all forgotten. It becomes completely and totally indistinguishable from any other covalent bond.
Let's go back to that ammonium ion. It has 4 bonds between nitrogen and hydrogen. Now, we know one of them was formed in this special coordinate way. But if you were to look at the final molecule, there is absolutely no way to tell which one it is. All 4 bonds are identical. Same length, same strength, same everything. The bond's unique history is totally erased. It's amazing! So, let's just nail down the key takeaways here. A coordinate bond is a covalent bond. Simple as that. But the electrons come from just one atom. For it to happen, you need a donor with a spare lone pair and an acceptor with an empty spot. But, and this is the coolest part, once it forms, it completely forgets its past and becomes just like all the other covalent bonds. It's just a really clever way for nature to build stable molecules. And that kind of leaves us with one last big idea to chew on.
If a bond's entire origin story just vanishes the second it's created, what does that really tell us about identity at a chemical level? It suggests that in chemistry, maybe it doesn't matter how you got there. All that matters is the final, stable state you're in now. Pretty deep stuff for a little chemical bond, right?